Welcome to the F1 Racing Team platform, powered by MonkDB. This environment represents a unified intelligence platform for race operations, analytics, AI pattern detection, and enterprise trust. Within a single system, we bring together SQL and NoSQL analytics, vector similarity intelligence, geospatial track movement, graph-based dependency analysis, time series telemetry, and enterprise governance, including audit and lineage. The result is a platform where race intelligence and data trust operate together. Think of this as the executive control tower and the engineering cockpit combined.
Here we see the executive control tower dashboard. This view summarizes the current race posture through key operational indicators. At the top are the primary race signals. Race status reflects the current phase of the race. Cars on track shows the active fleet currently transmitting telemetry. Pit recommendations represent strategy outputs generated from telemetry conditions and risk signals. The reliability index aggregates health indicators from subsystems, including brakes, power unit, and battery systems. Incident count tracks operational events that require engineering attention. Governance status confirms that policy enforcement across the system is active. Recent audit activity surfaces compliance and access records from the platform. At the center is the Race Health Gauge. This composite score combines real-time telemetry with operational incident pressure to reflect the overall stability of race operations. Next, the Strategy Recommendation Panel presents AI-assisted race decisions, each accompanied by confidence scores and explanatory reasoning. Below, the Live Alerts ticker displays threshold breaches and operational warnings in near real time. The leaderboard feed continuously updates driver positions as race telemetry evolves. From an executive perspective, this dashboard provides a single view of competitive position, operational risk, and decision readiness.
This screen represents the Telemetry Wall, the operational workspace for engineers and strategists. The multi-line telemetry chart tracks key metrics, including speed, tire temperature, and brake temperature across time. These signals allow engineers to quickly detect instability, overheating, or performance shifts. Next, the RPM, fuel usage, and ERS panel visualizes power unit behavior and energy deployment throughout the race. The sector candlestick chart provides deeper visibility into lap volatility. Rather than showing simple averages, it reveals the spread of sector performance, highlighting where drivers gain or lose critical time. The team comparison bars provide a cross-team view of pace versus reliability risk. Reliability gauges surface subsystem health signals for brakes, turbo systems, and battery components. This view brings together performance analysis and failure risk detection in a single operational plane. The outcome is faster strategy adjustments and fewer unexpected reliability issues during the race.
This module demonstrates track intelligence powered by geospatial analytics. The track speed heat overlay maps areas of high-speed concentration across the circuit. These hotspots reveal where drivers are pushing limits or where performance advantages are emerging. The leader trail minimap visualizes the evolving trajectory of the leading driver throughout the race. The live grid movement panel shows all cars moving across the track based on continuously ingested coordinates. An SVG race replay provides a visual reconstruction of the race grid as telemetry updates arrive. Behind the scenes, each coordinate is stored within MonkDB geospatial tables and indexed using geopoint structures. This allows spatial queries such as nearest car calculations, sector density analysis, and location-based performance insights. The result is a spatial understanding of the race, not just what is happening, but where opportunity and risk are forming on the track.
This screen displays the subsystem dependency graph. Modern racing vehicles consist of highly interconnected mechanical and electronic systems. Each node in the graph represents a component or subsystem, such as the engine, braking system, cooling network, or battery unit. Each component carries a health status and risk score derived from telemetry signals. Selecting a component reveals its dependency relationships. Downstream systems that rely on the component become immediately visible. The interface also surfaces related telemetry signals and historically similar incidents. This enables engineering teams to understand the blast radius of potential failures. Instead of reacting to isolated alerts, the system highlights cascading risk pathways. This dramatically improves mean time to diagnosis during race conditions. This section introduces driver intelligence powered by vector analytics. Rather than analyzing telemetry purely as raw signals, MonkDB represents driving behavior using embedding-based pattern models. These embeddings capture driving characteristics such as braking behavior, corner entry patterns, and throttle modulation. The similarity panel displays the drivers with the closest behavioral patterns to the selected driver. The cluster visualization groups drivers into driving archetypes based on their telemetry signatures. Insight cards translate these similarities into actionable racing insights. For example, drivers with comparable behavioral patterns may benefit from similar setup configurations or tire strategies. Through vector analytics, the platform moves from raw telemetry monitoring to pattern-level intelligence. This supports more informed setup decisions, coaching strategies, and race planning. This is the incident console, the operational memory of the racing system. Incident data and engineer notes are stored as semi-structured documents and indexed for fast retrieval. The console supports full-text search and filtering by severity, component, and time window. Searching for events such as brake overheating or pit window adjustments quickly surfaces historical records. Each incident entry includes severity level, affected subsystem, timeline context, and engineering commentary. This allows race teams to retrieve relevant historical context in seconds. Instead of searching across multiple systems, the platform consolidates operational memory into a single environment. The result is faster incident response and better decision support under race pressure. The MQL Workbench provides a flexible interface for interactive analysis. Analysts can write business-style filters using a simplified query syntax. For example, filtering for a driver with elevated tire temperatures after a specific lap threshold. The platform parses the query into an internal abstract syntax tree. The parsed structure and execution intent are displayed alongside the query results. Results appear immediately in tabular form, and the system automatically generates a visualization from the data. This allows analysts to explore race data rapidly without requiring complex SQL queries. Engineering teams retain full control through deterministic parsing and execution layers. The result is self-service exploration with strong governance guarantee. Next, 3 analytical queries demonstrate how MonkDB processes race intelligence directly from operational data. The first query computes a vehicle health score from recent telemetry. It combines signals such as brake wear, turbo health, battery condition, and tire temperature into a single reliability metric. This helps engineers quickly identify cars under mechanical stress before failures occur. The second query analyzes race pressure across track sectors. It combines geo-coordinates with telemetry attributes like speed, vehicle density, and sector information to identify where competitive pressure is building on the circuit. This reveals high-risk zones and overtaking opportunities across the track. The third query compares team performance across races. It calculates average speed and average risk score for each team, creating a benchmark between pace and reliability. This helps teams understand which competitors balance performance and stability most effectively. The final section presents the enterprise trust layer of MonkDB. The governance panel manages data access policies across the platform. Policies define which users can access specific datasets, which columns are masked, and which roles are permitted full visibility. These policies are enforced directly at query time. The audit console records every data interaction across the system. Each record includes the user identity, dataset accessed, timestamp, module origin, and whether the request was allowed or denied. This provides a complete compliance trail for operational decisions. The lineage view traces the full derivation path of data. Source events, pipelines, models, and resulting dashboards are connected through lineage relationships. This makes it possible to explain exactly how any metric or insight was generated. For regulated environments, this level of transparency is essential. It ensures that insights are not only powerful, but fully explainable and accountable. MonkDB's core differentiator is unification. Operational telemetry, geospatial intelligence, analytics, vector pattern recognition, graph dependencies, governance, audit, and lineage all operate within a single platform. This architecture eliminates fragmented data systems and reduces integration complexity. The result is faster operational decisions with provable data trust.